screen share.
Okay, great. Yeah, hi everyone. I'm Nick Bronn. I've been at IBM Quantum for 9 years now, and I was originally an experimental physicist. So I used to work on developing the hardware, doing measurements in the fridges, banging things with torque wrenches, designing the cutting edge hardware that kind of is going into the stuff today. But for the past 2 or 3 years, I've been kind of working on the software side, a little bit more applications, a little bit more enabling Qiskit as a research tool for people to do things such as, pulse level transmon physics or quantum simulations and stuff like that. So yeah, so that's kind of my background. So I'm going to talk about a lot of different things today, and let's see if I can just share this real quick. That looks right. Okay, I guess you can see that. And I guess if there's any questions, I would be happy to have Michelle interrupt me. So feel free to put them in the chat, and I'll keep going. I'll try and take pauses when I've explained some things so that we can have time for a conversation here. All right, so whenever I start talking about hardware, I like to always kind of go back to thinking about why do we do quantum in the first place? What is the difference between the information in the physical system that obeys quantum physics versus classical physics? And then in particularly move to that of superconducting qubits, which is how IBM Quantum does builds their hardware. And so those have some overviews. I'll give you an overview of what superconductors are, what our superconducting qubits look like, and how we control them with microwave pulses. And then we have the quantum processor itself, but then we also have a lot of supporting architecture that usually doesn't get talked about too much, but is important for actually not just superconducting qubits, but for all kinds of quantum systems because of the signals you need. And we'll go through the roadmap and talk about what IBM's plans for the next few years are. And then I'll tell you a little bit about error mitigation and the kinds of things we're trying to make it easier for the researchers and the users to use our systems and to squeeze the most out of our current noisy systems. So 40-ish years ago, IBM and MIT co-hosted the first joint Physics of Computation conference. And if you look at this picture, you can see a few people. I don't know if you can see my mouse or not, but if you can see Richard Feynman in the back, for example, and IBMer Rolf Landauer in the front, and Charlie Bennett, who is still with us today, is one of the fathers of quantum information theory, is actually taking a picture. He just won the Breakthrough Prize for quantum information along with 3 others a few weeks ago. So that's congratulations to him. But you might ask why IBM cared about the physics of computation way back in the day. And this is early 80s. Why were they employing physicists such as Rolf Landauer and Charlie Bennett? Well, it's because a lot of people have the same questions they have today about computation. It's like, there's their fundamental energy limit to the computations we do, such as, like, say, doing all these kind of AI type things or mining Bitcoin or whatever. We know that computation can take up a large amount of power. And it turns out there is a fundamental limit to irreversible quantum computing, which is how classical computing works. And there's this limit's called the Landauer-von Neumann limit. And it's a very, very small energy cost that's required to reset the classical bits. It turns out people kind of realized at this point, well, if you had a computer that obeyed quantum mechanics, the evolution of that computer would be unitary, which would be reversible, and it would not be subject to this fundamental limit. So kind of the ideas of doing quantum computing, the thermodynamics of what quantum computers might look like were developed at IBM. Along the same time, Feynman was kind of the first person who said, I wish I had a quantum computer because then I could program my quantum problems into it and be able to find the solutions much easier. And so that's how the motivation kind of started and how IBM kind of got into that place in the beginning. So what does a quantum bit look like? Well, I always go back and think about what does a classical bit look like, or what do we do with classical computers? And there's a number of physical systems you can represent classical information in. These are 3 of my favorite examples, such as the on-off of a light switch, whether current is passing or not passing through a transistor, or the polarity of tiny magnets in a hard disk drive. For example, these represent the logical states 0 and 1 because they are somewhat latching. They're nonlinear. Like, it's always kind of you always kind of push to the on or off position. There's a threshold voltage on whether the current is flowing or not through the transistor, and there's a certain critical fields you must apply to switch the polarity of the magnets. So it's pretty nonlinear. It's not as analog as like a quantum system. And in a quantum system, the thing that makes it analog is, well, I ask the same question: can I encode my 0, 1 in the ground or excited state of an atom, for example, or the up and down states of an electron, or maybe in the charges of tiny superconducting charges? The answer is yes, you can. And then because whatever state represents the 0 and whatever state represents the 1, those will both obey Schrodinger's equation. And since Schrodinger's equation is a linear equation, any superposition of those two solutions will also be a solution of Schrodinger's equation. So in this way, we get the block sphere, where we take any complex superposition, we normalize it so that the coefficients on those states have a probabilistic interpretation. Then we get this block sphere picture where there are zeros at the North Pole, the ones at the South Pole, and then any state on the surface of the sphere is a superposition where the probability is represented by the amplitude of that. So if you're like on the equator, for example, you have a 50-50 probability of measuring 0 and measuring 1, because when you perform that measurement, you collapse it back down into the classical state. Okay, so what do we do with that? Well, we'll go to superconducting qubits, but before we go to superconducting qubits, let me just tell you a little background about superconductors, which is actually outlined pretty well by this wonderful NOVA documentary called The Race to Absolute Zero, where there's a discussion about these two guys, James Dewar, who was a scientist in the UK, who was thought to have cooled down and liquefied the last remaining gas, which was hydrogen, which liquefies at a temperature of 20 Kelvin, where 0 Kelvin is about -273. So 20 Kelvin is 20 degrees above absolute zero there. At this point in time, it was just kind of been aware that there was another element called helium that exists, but they didn't think many resources were left on the Earth. They were found as spectroscopic signatures in the sun, so they figured it just exists in the sun. But eventually, people realized that they were left over in geological structures from radioactive uranium decay. An alpha particle is the same as a helium nucleus. So when alpha decay happens from uranium, it can pick up a couple electrons, become helium, and become trapped underground in deposits and mined out. And if you watch this video, it's on YouTube, you'll find that there's another guy, Heike Kamerlingh Onnes, who was a competitor to Dewar, who was in the Netherlands. They were head-to-head competitors in this field. And he was actually the first to be able to liquefy helium. For one reason is he was able to get helium. He was a much more collaborative kind of scientist, and helium was kind of a rare thing. It was still, even though they found deposits in geological formations, it was still hard to get. So he was able to get the helium and liquefy it, and that liquefies about 4 Kelvin, so about 16 Kelvin cooler than hydrogen. But the same kinds of processes, they went through the same. What became really interesting is what you do after you achieve liquid helium. And if you're any kind of physicist, what do you do with something when you get it cold? You throw some metals in it and see what happens. You measure their properties. So in particular, he measured the electrical resistance of different materials as a function of temperature, and he found superconductivity. So if you remember your kind of condensed matter physics or your thermodynamics, you might remember that the resistance of a material goes down as the electron-electron collisions go down and the phonon modes go down. But you expect it to retain some residual resistance even at 0 Kelvin. Now, for a superconductor, what happens is that resistance continues down, but you reach some point called the critical temperature, or TC, in which it completely drops to 0. So these metals lose all electrical resistance. And that is kind of a weird thing. And this was especially a weird thing in 1908, because it wasn't even explained until about 50 years later, the microscopic theory of why this is, which I'll explain on the next slide. There's another effect too called the Meissner effect, where the superconductor behaves as a perfect dielectric in which it expels all magnetic field. And so if you're above the critical temperature of the metal, it allows a magnetic field to penetrate. But as soon as you drop below the critical temperature, it will repel that field and force that field to go outside of it, which is why kind of like magnets and superconductors repel each other. And so you can get like magnetic levitation, for example. So these are kind of the two big takeaways for what superconductors do. Another one, I think, is that there's a lot of metals that become superconductors. So if you look at the periodic table, all these ones in browns are superconductors at ambient temperature pressure, and the purple ones become superconductors at high pressure. So a lot of common elements, like the things we make superconducting qubits out of, say like aluminum and indium and lead and mercury, Mercury being the one that Onus discovered, became a superconductor at 4 Kelvin. Titanium, niobium, et cetera, they're mostly superconductors. It tends to be the magnetic elements and the noble metals that do not become superconductors. But you kind of see superconductivity as more of the rule than the exception. So I think that's kind of interesting. I'll go ahead and say here that these are metallic superconductors. They typically become superconductors below about 10 Kelvin or so. Niobium with one of the highest TCs at like 9 Kelvin. You can get alloys that maybe superconduct up to 20, 25 Kelvin. And then there's a such things called the high temperature superconductors, which were discovered 35 years ago, actually also at IBM. And we still do not to this day have a microscopic theory of why they work, which is kind of interesting. And maybe we can use quantum computers to solve that. But as an aside, let me tell you how the ones work that we know how they work, which we'll call low temperature superconductors. Basically, the electrons effectively become attracted to each other, and they form these pairs we call Cooper pairs. Now, electrons are both negatively charged. Their Cooper pairs are named after, or Sheldon Cooper was named after the Cooper pairs, Leon Cooper, who discovered those. Normally, you don't expect electrons to be attracted to each other since they're both negatively charged, but they have an interaction that's mediated by a crystal lattice. So for example, you can think of a metal as being a bunch of electrons in a gas that reside in this residual lattice of positive charges. And so when these electrons are flying around, they can leave a wake of positive charge, which physicists call a phonon, in its path. And then when you have, say, the left moving electron has a wake following it, it will attract the right moving electron and effectively cause an electron-electron attraction to occur. And so that's kind of the microscopic idea, and that was what was figured out kind of in, I think, 1957, which won the Nobel Prize because you were finally able to explain these kinds of things. Other interesting things about superconductors are they kind of exist similar to wave functions. They're kind of like macroscopic quantum states in that they have conjugate variables, such as the number of Cooper pairs that form inside of the metal, and the superconducting phase. So a superconductor on its own is all a single phase, and you can even write it like a wave function. And these variables are actually just conjugate variables as well. So you can't measure for example, the phase and the number at the same time. They have this commutation relation, which is exactly similar to the Heisenberg uncertainty principle for position momentum. So in that way, it kind of you can be informed about the ways you can go about building superconducting qubits out of these things and understanding them in terms of good quantum numbers, for example. The other thing that's important about quantum computers or superconducting qubits is this element called a Josephson junction. Basically, you have these supercurrents that flow through these as these Cooper pairs through the superconductors, but you can have barriers there. For example, an insulating barrier, it can be a metallic barrier or a ferromagnetic barrier or whatever, usually insulating, where you can have quantum tunneling going through that barrier as like a potential well, and then you might have less amplitude on the other side. But these Cooper pairs can tunnel back and forth, and this element is called a Josephson junction, and it's a very important element, and I'll show you why that is. And so maybe now's a good time to see if there's any questions in the audience. How are we doing?
I think we're doing fine so far. No questions.
All right, great. And I'll just keep going then. Okay, so basically the evolution of superconducting qubits started, the first one was discovered in 1999. I'll show you a picture of that in a sec. And they're characterized kind of by the regimes that they exist in. You're allowed to, because these are circuits, these are designed as superconducting circuits, you're allowed to build their parameters. And so you can kind of control the quantum states by engineering. And so there's two fundamental energy scales that we think about when we talk about superconducting qubits. That's the charging energy. That is the energy it takes to add a Cooper pair to a superconductor, given by the kind of charge repulsion, and the Josephson energy, which is the energy that's stored in the current that goes through the junction. So kind of like an inductive energy in a way. And you can tune the type of qubit by looking at these ratios, and you can also apply magnetic flux to realize different kinds of qubits. So the first one that was done is the charge qubit. Here, the good quantum number is the charge, and that's either there is or isn't an extra Cooper pair on this little tiny island, which exists on this, it's called a box in here, separated by two junctions. So this is like a potential well, like up in this picture, where you have the zero state represented by when you have a Cooper pair trapped on that island by this line here, which is inside the well, or when there's no Cooper pair on the island, which is represented by this 1, which means it can escape the well. It has enough energy to fly away. So that is using the charge quantum number as a good quantum number for your qubit. You could also use the phase quantum number and design something called a flux qubit, which is usually a loop, which is where your quantum states are propagating supercurrents to counterclockwise or clockwise, kind of separated by this kind of picture here. And you have like one localized to the left, one localized to the right, and those are going to be affected as a function of flux or phase across the junctions. And then likewise, you have another type called a phase qubit, where the phase is also another good quantum number. And you have something similar, but you have a different kind of readout scheme where it's easy for you to kick out the higher level 1, and you can get a voltage response as you do that. Pardon me. So these are all using one of the good quantum numbers as the state of your quantum system. But as you can imagine, if you're in one of those states, you might be like if you're a charge qubit, you'll be very susceptible to charge noise. If you're a flux qubit, you're going to be very sensitive to magnetic flux through the loop, for example. So one of the things you can do is you can actually remove yourself from being in a good quantum number. And that's what we do for the transmon superconducting qubit, which we use at IBM, where essentially we increase the EJ over EC ratio, where we're kind of like a charge qubit, but we get immunity from charge noise. And you'll see on the next slide as we go through, we're storing the quantum information as oscillations in our superconducting qubits. So what are our superconducting qubits look like? Here we have a bunch of superconductor on top of the silicon substrate, and we have patterned into it 5 qubits, which are inside of these square boxes. The qubits themselves look like these equal signs that are rotated by 90 degrees. In fact, those equal signs represent the capacitance. Those are two pieces of superconductor with a field between them, so it's essentially a capacitor. And then a very small piece between them is an aluminum oxide, aluminum Josephson junction. So that forms a superconductor, an insulator superconductor, which is formed in a stacked layer. And that Josephson junction, I didn't tell you this before, but electrically it acts as an inductor, but it acts as a nonlinear inductor, and it's a dissipationless nonlinear inductor. So the important thing is you don't want to have any dissipation, because then your quantum information goes away. And this nonlinear feature will be shown to be an asset in just a moment. The other thing we have going on here is we have these superconducting microwave resonators. So these are like coplanar waveguide microwave resonators. Basically, that just means these are like the coax you have at home for your cable TV, but it's flattened out so it's in 1 dimension or 2 dimensions. So you basically have like a center pin in the middle here, and then you have ground planes on either side. So in that way, it's kind of like the pin and the sheathing of your cable coax at home. And these do a lot of things, actually. We use them to couple the qubits together so that we can entangle them. So we can actually, I'll show how this works later. We can use these as filters because they're typically detuned in frequency from the qubit frequency, so that will suppress radiative loss. And we can also read out the quantum states using these kinds of things in a manner we call circuit quantum electrodynamics, and I'll describe that as well later. So these things are very, very kind of useful, and this is a common architecture for transmons to build superconducting qubits out of transmons. So basically, both these superconducting microwave resonators and the qubits are kind of like oscillators, but the difference is the distributed, like the waveguide resonators, are more like a linear LC oscillator or a harmonic oscillator. And the thing you want to notice about a harmonic oscillator is that you can look at the energy level states and they're equally spaced. So if I was to label the ground state as 0 and excited state of 1, then I have this energy difference and I could try to drive between those two, but then I wouldn't be able to distinguish between the 1 and 2, the 2 and 3, 3 and 4 state. So I'd end up driving from 0 to 1 into all my other states, and I would smear out my quantum information. So it doesn't really make a good qubit. However, because my Josephson junction is nonlinear, it's a nonlinear inductor, I have an anharmonic oscillator in this case, which means my energy levels are spaced differently. So my energy level spacing between 0 and 1 is different from 1 to 2, it's different from 2 to 3. So in that case, I'm able to use the frequencies there and drive between 0 and 1 as, and treat that as a qubit and pretend like the other states don't exist. So, for a lot of ways, you could just pretend that the 0 and 1 qubits are all you have, because you're just going to be driving those on resonance, and that resonant frequency is given by about 5 gigahertz. There's a natural spread to these frequencies because the microscopic details of these Josephson junctions are going to differ from qubit to qubit. And so the critical currents are going to vary, and that means the frequencies are going to vary, which is actually a good thing. We need the frequencies to vary, and you'll see why on another slide. What does the energy correspond to? So 5 gigahertz here is, if you multiply by Planck's constant and divide by Boltzmann's constant, that corresponds to a temperature of 240 millikelvin. So that is substantially less than the critical temperatures of even these superconductors here, which are a few Kelvin. We need to be substantially colder than 240 millikelvin, because if we're not substantially colder, we'll have a lot of thermal broadening in our 0 and 1 levels, which will add uncertainty about the frequency, which will add fluctuations, thermal fluctuations to our qubit, which causes dephasing. So it will make the coherence between our superpositions go away. And so that's a bad thing for quantum computers. So you want to have it substantially colder. We have fridges about 10 millikelvin, and that's kind of why we want everything so cold, even when we're dealing with these higher, order energy levels or in higher order thermal levels. Okay, how are we doing so far? Any questions? That's kind of the hardware, but I'm going to go into the control next if there's nothing else.
Hi, Nick.
Hey.
Hi, I have a quick question. So,
sure.
How do we know whether superconducting material is a good candidate to make a qubit?
That's a great question. So one thing is we can look at the quality factor of the resonant structures that we make here. So for example, you can look at this, you can pattern these resonators, and you can look to see how much the photons that when you ring them up, how quickly the photons decay out of that structure. Some of that you can engineer, but some of it is due to the defects in that material. So you basically want to be able to have a high quality factor or high Q material. That's kind of the one materials aspect of it. Another aspect is the ease of fabrication. So dealing with metals is actually pretty easy, but if you want to go to high temperature superconductors, they're typically made out of ceramic oxides, which are much more difficult to pattern and deal with than metals. But you do always have to start with essentially a high quality metallic film. And then you'd be able to grow a controllable oxide on it that doesn't have that many defects as well. So great question.
Okay, thank you.
Thank you. All right, Akela, so I'll keep going on then. Okay, so let's talk about our control and measurement of the superconducting qubits. And like I say, I always go back to the basics when I go through these things, because it's always good to ground yourself in what you maybe learned in your class, for example. So we got the Bloch sphere here. We've got 0 at the North Pole, 1 at the South Pole. These are our computational states, which we write as 0 as 1 because we're lazy physicists, but those actually stand for the column vector 1, 0, or the column vector 0, 1. And you can consider measuring along the axes, the X, Y, and Z axes, which are represented by these operators, and the measurements are the eigenstates and eigenvalues of these measurements. In particular, you'll see for this case, for superconducting qubits, we measure along the Z-axis, and you'll see the Z operator, the 0 and 1 are eigenstates with eigenvalues +1 and -1 of that operator. But they also do another important thing is these Pauli matrices generate rotations around the Bloch sphere. So you might have seen this equation if you took quantum mechanics, but this is basically gives you the unitary matrix that executes a rotation by an amount theta around a normal unit vector of n, which is given by this exponentiated thing of this unit vector n dotted with the Pauli vector of Pauli matrices, which is more easily calculated with this cosine and sine expression, which still maybe looks a little complicated, but it's actually pretty easy to use. If I'd say want to talk about a rotation of theta around the x-axis, I just put my x Pauli in there and do the math, and I get this unitary, which is the unitary that actually executes the revolution of a theta around the x-axis. So I can start to represent my gates or my operations as these rotations around the Bloch sphere, which is how I kind of do it, because I think it corresponds nicely to what you actually implement physically. And so what do you actually implement physically? You hit these things with microwave pulses that rotate the qubits around the Bloch sphere. So you impinge like a pulse that's shaped with a Gaussian envelope with a carrier frequency of that 0-1 transition frequency I talked around, like around 5 gigahertz. And what that does for you is it gives you a rotation in a axis in the XY plane of the Bloch sphere. So if I have one microwave pulse that rotates around the x-axis for me, in this way, I can just shift that thing 90 degrees out of phase, and it will rotate around the y-axis for me. So in this way, I can actually continuously realize any rotation in the xy plane. But then you might wonder about the z rotations. And you can generate z rotations out of x and y rotations combined, or you can actually get them for free, because what the z rotations do is actually just shift the phase of the subsequent pulses that you are going to execute. And if you do this, then you can look at the average single qubit error as determined by randomized benchmarking and see that, in fact, when I don't do a lot of my gates, I get a lower error rate. In fact, I like to say these z rotations happen in software. They take 0 time. They have 0 error. The only perfect quantum operation is the one that you don't actually do. So that's how we actually realize z rotations, because we don't need to actually execute them. We just compile things differently later in the circuit. That's a trick we actually discovered, 5 years ago. So that's how we do it. I think that's how that's become pretty commonplace anyway at this point. So that's single qubit gates. For 2 qubit gates, I like to bring us back to classical computers. And so you might have heard of something called a universal classical computer. Well, what does that mean? It means you have a universal gate set. I can execute any arbitrary Boolean algebra equation given in either one of these classical components. So I don't need either the not and or the not or gate. Either one of these works. I can build a arbitrary Boolean logic out of these. And you'll see that these are given by the truth table. You have 2 inputs, say 0 and 0, 0, and not that is 1, 1 and 1 is 1, not that is 0, or vice versa, like for the NOR gate, 0 or 1 is 1, not that is 0, so on and so forth. And that will allow me to realize any Boolean algebra or Boolean equation. The same kind of exists for quantum computers, is I want to be able to represent any kind of special unitary quantum operation, which can always be broken down into single and 2 qubit gates. In fact, we don't even need every single qubit gate to do it, but I just showed you we can do any arbitrary single qubit gate. But there's special 2 qubit gates that we need that kind of make this universal quantum computing, meaning that we can execute kind of any quantum operation. And you can choose any one of these as well. The one that we choose or we use at IBM is related to a controlled knot. So that's kind of also maybe a popular one that you might have seen in your class. This is basically where we have a control qubit, which is the first qubit, and the target qubit is the second qubit, and we do a knot on the second qubit if the first qubit is a 0. So if you have 0, 0, nothing happens. You go to 0, 0, 0, 1, the control's still in 0, 0. You get 0, 1 as the output. But when my control qubit's in 1, we flip the target. So 1, 0 goes to 1, 1, and 1, 1 goes to 1, 0. Now, you can use other gates, such as a controlled phase gate, where you just get a -1 or a phase of 180 degrees in the case when both qubits are in the 1 state. Or you could use an I swap, for example. This is where you switch the information in the two qubits, and if something actually gets moved around, you get an I in front of it. And you can realize all of these with superconducting qubits, but we typically choose one of them. And then a couple things I'd like you to notice about these is that you can kind of see how you get entanglement out of these gates. If you were to take the control and put it in a superposition, say you'd make 0, 0 plus 1, 0 by doing a Hadamard on the control gate. Then when I apply the C naught, I would get 0, 0 plus 1, 1, which is a maximally entangled Bell state. So you can kind of see just from this truth table where entanglement comes from. You could do it with the other ones as well. Or similarly, the other thing I would like you to see is that there's 2 outputs for 2 inputs in every quantum gate, but there's only 1 output for every 2 inputs, which means that this classical computation is irreversible, because I give you the 1 output of a NAND gate, and you couldn't tell me you couldn't tell me what the inputs were. But if I give you the output of any one of these 2 qubit quantum gates, you can tell me what the 2 inputs were. And that shows you that classical is irreversible and quantum is reversible. Okay, so how do we actually realize this? Well, we use something called cross resonance, which is effectively a ZX operation. So this is the kind of interaction you can generate between 2 qubits, and you can understand it like this. I can take my Z Pauli matrix and my X Pauli matrix and tensor them together to generate this 4x4 matrix, and then throw it in that equation I showed you earlier, and you get this 4x4 unitary matrix that describes the evolution of the of the different states, which are typically denoted as a column vector 0, 0, 0, 1, 1, 0, and 1, 1. So what that means is, if I look at this top left part of this matrix, that is a rotation of the positive theta direction when the control qubit, in the subspace in which the control qubit is in the 0 state. So when my control qubit's in 0, I get a plus theta rotation. But when I'm in the lower right, that's the subspace in which my control qubit is in the 1 state. That is a rotation around the minus theta direction. And so basically what I'm getting is I'm getting rotation of the target qubit, and the direction depends on the state of the control qubit. It depends on which subspace you're in. And so if we look at the block sphere to see what happens to like each basis state, we can see if I prepare my, my purple states, let's start with, I prepare my control qubit in the 0 state and my target qubit in the 0 state in the purple, and apply the cross resonance, I'm going to rotate to the right, for example. Now we forget about that, and let's prepare our control qubit in the blue state. So in the 1 state, and my target qubit's in the 0 state, and I apply that, and the blue goes to the left when I apply the cross resonance. So basically what happens then, if I take my control qubit and repair it in a superposition of 0 and 1, what I get when I apply the cross resonance is I'm rotating my target qubit in both directions, because the control qubit's in a superposition. And this is achieved, which I'll show a little bit more, by applying a control at Q2 onto Q1. So we'll break apart that physics a little bit more, because it's fun to understand if you're into device physics. And one of the reasons we like the cross resonance gate so much is it's an all microwave entangling gate, which means I turn it on and off with just microwave pulses. There's no separate flux bias lines or any kind of currents you need to apply. It's just microwave pulses. So that makes things a little bit easier to understand. And what we're going to do is look at this 2-qubit device here, where we used to do a lot of research on gates on. And let's just pretend like this bus doesn't exist here, so we're uncoupled. And so if we just have 2 qubits that are in isolation from each other, we can realize our energy level diagram by thinking of both of them in the ground state as being this lowest level, the control qubit being in the excited state by this red in 1, 0. So this is the frequency of the control qubit. We can think of the frequency of the target qubit as omega 2, the 0, 1 being in this level. So now, because these qubits have different frequencies, we denote those difference in frequencies by delta, which is very important because we want to have the difference in frequencies so they're addressable in our scheme here. And then when both of them are in the excited state, they're in the 1, 1 state. So this is the energy level diagram. And if I was to take this and I was to add this microwave bus there that's already there, it presents a coupling we call J, which is just a coupling rate between the qubits, typically around 3 megahertz, whereas delta is typically around at least 50 megahertz or so. So there's a very, very small shift in the energies between these things, and these qubits become slightly hybridized. Very, very slightly, because J over delta is very much smaller than 1. But this basically means the control qubit stays mostly like the control qubit, but becomes a little bit like the target qubit. And an excitation of the target qubit is mostly like the target qubit, but becomes a little bit like the control qubit. And this is kind of, so this is a very slight hybridization we call the dispersive regime. And that's how we kind of understand things, because it's kind of easy for us to understand these things being slightly coupled to each other, but you can generate like effective Hamiltonians to deal with the to deal with what the control gates do to the system. So if you want to manipulate the system, you can always manipulate Q1 at its on resonant frequency, which is the on resonant 0-1 transition frequency to do single qubit gates. You can do on resonant single qubit gates to Q2 by applying Q2 omega 2 to Q2. But if you want to do the 2 qubit gates, what you do is you apply a frequency of omega 2 and drive Q1 with it. So in effect, you're driving the part of you're driving the target part of the small amount of target that the small amount of the control qubit that is like the target qubit. Or if you look at the energy level diagrams, if your control's in the 0 state, then you're driving around the orange in this Rabi oscillation. But if your control's in the 1 state, then you're driving around those Rabi oscillations in this green state. And because there's a sign difference between these states, that actually generates a rotation that's kind of, or that is in the opposite directions. So that's kind of the most physicsy we'll get today, but that's how the cross resonance operation works. And we generate these ZX operations. If we get to ZX pi over 2 rotation, then we add some single qubit gates, and we can build a C0 out of that. So that's how 2 qubit gates work. And maybe I'll just see if there's any questions on that real quick.
Yes, I will actually ask some questions, I think. I think earlier in the picture, so you mentioned this idea of superposition and entanglement. Like in this diagram right here, like, do the qubits need to be entangled for this to happen? And like, what's the difference between those two ideas of a qubit being in a superposition versus an entanglement for this scheme to work?
Oh, that's great. So this scheme always works, actually. So if you, in fact, what you usually do for calibration is you would prepare the qubits in the 0-0 state, and you would apply this cross resonance, and you would look at the oscillations and try to understand what was going on. But you would also prepare the 1-0 and look at these oscillations. Now, these aren't entangled at all. These are completely separable because the control is in an eigenstate of the ZX operation. However, if you wanted to take this and put this in a superposition of, say, 0-0 and 0-1, then you would effectively be driving cross resonance between these two, and that's how you would generate entanglement.
Oh, I see. Okay, so it's like corresponding to different pairs.
Right, exactly. So each one on their own, the orange one is separable, the green one is separable. But if your control is somewhere, a superposition of 0 and 1, then you're kind of doing both oscillations at the same time. But when you characterize them, it's hard to make sense out of things when they're entangled. So you want to prepare them in separable states, so you can consider how the cross resonance affects your target qubit in the two cases separately. And this is a very common experimental technique we use called Hamiltonian tomography. And if you're more interested in it, me and this postdoc I work with wrote the chapter in the Qiskit textbook on it.
Oh yeah, if you could send a link after, that'd be cool to read.
Yeah, absolutely.
Okay, then you also mentioned this idea of a flux bias. What does that mean?
Great question. So if we look at, so one of the things I didn't spend too much time on because is that when you have these superconductors and they're arranged in a loop right here, the amount of phase difference across that loop is quantized. And it also depends on the magnetic field that's going through that loop for some very specific reasons. So your overall magnetic field will give you an overall global phase difference. And then across these phases, across these junctions here, there can be phase jumps as well. And those phase jumps determine the critical current passing through those junctions as well. So all these things are kind of related. And when you have like a frequency of this qubit, for example, you're typically biasing that qubit with a magnetic field. So any noise you have in that magnetic field, or you might be applying a direct current to it, for example, any noise you have in that magnetic field or from that current source that's providing the magnetic field is going to manifest itself into changes in that frequency. And so, like I said for earlier, when you have the thermal broadening, that's essentially like thermal noise on top of the levels of your qubit. Just like that, the magnetic noise, like in this magnetic flux noise, will generate noise on top of the levels of your qubit, and essentially that provides you dephasing. So that you'll lose in decoherence time because of the dephasing of your qubit, which means your essential coherence between your 0 and 1 state will go away.
I see. So it's like in that scheme, whenever you wanted to rotate it to that like ideal position to apply the cross resonance, like it wouldn't be exactly in the position that you want it to be because of the magnetic field noise.
Right. I mean, it's not just that, but just inherently, if the qubit was even on its own, it would be susceptible to magnetic field noise. And the thing for the cross resonance to work is we have fixed frequencies here. And the reason why we can get away with this is because we have different frequencies. So we can address this target via the frequency at the control qubit. And so all we need to do is make sure we can control these qubits. I mean, there's a lot of stuff that needs to go on here, but basically these frequencies need to be well isolated so that we can address them well. And because we don't have to tune these things on resonance like you would if you did have flux qubits or other flux tunable schemes, because you can operate flux tunable transmons as well. You can change the frequency, but that tends to introduce noise. Now it's kind of a trade-off. You can do things faster also if you make them on resonance. So if you do things faster and you're more susceptible to noise, you ask the question, is it better than having long coherence qubits with longer operations? And everyone can write papers in the literature and argue about which is better, but we like this one the best.
Gotcha. And just for everybody, coherence time is like the amount of time that I think the qubits are in that state. And
Right. There's kind of two time scales here. There's a relaxation time, which is if I ask myself the question, it's if I prepare the qubit in the one state, how long does it stay in the one state? And that's kind of like radioactive decay. Like after a T1 amount of time, that's kind of like the half-life of the qubit. And then the decoherence time takes into account relaxation and dephasing. And dephasing is how noisy does it get between 0 and 1? Like when I have a coherent superposition, how coherent does that stay? And so it's also very important for quantum computing.
interesting. All right. Well, thank you, Nick, for answering all my
No
questions.
problem. Of course. Anytime. Okay, so for measurement, I'll kind of describe what goes on here. We have a computer that tells you to do a measurement pulse. We do our measurement pulses at about 7 gigahertz instead of 5 gigahertz, so somewhat detuned. They're generated by radio frequency synthesizers and arbitrary waveform generators, go down into a dill fridge. They get filtered and attenuated and all that stuff down, and then interact with a resonator, which collapses the state of the qubit into a 0 or 1. And depending on whether that collapses into a 0 or 1, it imparts a different phase shift onto that pulse. So basically, we'll watch it one more time, I guess, just to the main thing that what happens is we ring up the readout resonators that are connected to the qubits, which collapse the state, and they impart a state-dependent phase shift on these signals. These signals then leave the qubit chip and are amplified using some very special amplifiers I'll talk about a little bit later, and come out of the fridge, and they are then, large enough signals. They go from like, tens of photons or something like that to a signal that you can measure very easily with a computer. We mix it down to an intermediate frequency that can be digitized easily, and we integrate and discriminate them so we know what these what the measurements actually are. So then, in a nutshell, that's just kind of a cool animation of to show you what the measurement signals look going in and coming out of the fridge. Okay, so I'm going to talk about some of that architecture now, if there's no other questions. Sometimes at IBM, we like to take these fridges, these kinds of things out of the lab and put them into fancy 9-foot by 9-foot by 9-foot square boxes and kind of hide all the components away so that it just looks very futuristic and cool. And so this is one of the research prototypes, IBM Quantum System 1s we have in Yorktown Heights in the lab there, but there's also one in Germany and one in Japan. So I'm a hardware guy by training, so I like to look under the hood and see what's there. And what I see is something called a dilution refrigerator. And in particular, this is something called a dry dilution refrigerator. So basically, if you want to get really cold, you have to be pretty cold beforehand. And so back when I was in grad school, the first step of getting anything really, pretty cold is to dunk it in liquid helium, which is at 4 Kelvin, which is what Onus cooled down, 1908. And it's really kind of a pain to deal with. So what this dry dilution fridge allows us to do is it has a closed cycle helium-4 pulse tube compressor that allows the cooling of this upper plate to 50 Kelvin and this next upper plate to 3 Kelvin. And what you've got to know also is when we put all these cans here and we are operating this thing, and we put it under vacuum, so we suck all the air out. And when it gets cold, all the thermal connections between these plates are broken. So they're essentially thermally isolated. So once we're at 3 Kelvin here, that's essentially cold enough to do the dilution cycle, which is the fancy one. And that is where we use a mixture of helium-3 and helium-4 to do the rest of the cooling. And the interesting thing about that is that helium-3 is a fermion and helium-4 is a boson. So quantum mechanically, they're different. So when we get them cold enough and we liquefy them, they separate like oil and water in this little section called the mixing chamber down here. And so what we actually have is this 2-stage cooling process where we pump helium-3 through the helium-3 rich phase, which is a quantum fluid, through the helium-3 phase, which is mostly just a helium-4 superfluid, and then out through the still, where it gets recycled by some gas handling, some pumps and stuff like that, and recompressed and put back in. And then it exchange heat with the outgoing helium, so it's cooled on the way in as the helium-3 goes out. And we're able to get these stages down. Essentially, this is usually around 800 millikelvin, 100 millikelvin, and 10 millikelvin. And then we put all the quantum stuff down here, down at the very, very bottom. So it's thermally anchored, which means it's connected via copper, which makes a good thermal connection. So this is all down at 10 millikelvin. And so basically, you can think of everything inside of this fridge that you're looking at, it's either to do one of two things. It's to deliver signals to and from the qubits, or to get things cold. And so the things you want to do there is like, in addition to getting things cold, you need some very, thermal cryogenic stability, because you don't want temperature fluctuations. You need to make sure I/O is very good. Your signals are isolated and routed in the correct directions. You have amplifiers for the measurement signals that are doing a very good job without hurting the qubits, for example. So that's what's inside the fridge, and we'll explore that a little bit more too. And then outside the fridge, we also have, in addition to the cooler, in addition to the gas handling unit, which is behind this, which I'm not showing, we have the control racks. So these are analog microwave components based on FPGAs that do the shaping of the microwave pulses. We mix them with stable microwave sources, and we can digitize the signals that come back out, and we custom build these kinds of things. And actually, this was like a 20 qubit device originally. And we call these like pizza boxes. This is an older generation of electronics. Each one of these pizza boxes could control essentially a qubit, control and measure a qubit. And so one of the things you've got to do is shrink these kinds of things down, because we're building bigger and bigger systems. So some of the things that we actually spend our time working on in the lab, and some of the stuff I've had to do with, is looking at how these quantum limited amplifiers. So these are a very special kind of amplifier that are also based on the Josephson junctions. In particular, the Josephson junction has this nonlinearity, which is very important, that we build an anharmonic oscillator out of it for a qubit, but that nonlinearity can also be used to build amplifiers. And so there's two kinds of quantum limited amplifiers. And when I say quantum limited, I mean they add the minimum amount of noise that's mandated by quantum mechanics, which is half a photon at the readout frequency. And they add about 20 dB of gain. So that's like 100 times the amount of gain, which is a huge amount of gain, especially at 10 millikelvin. And they do it using the nonlinearities in a bunch of Josephson junctions. So we have two kinds, called the traveling wave parametric amplifier, where the signal gets amplified through this kind of metamaterial of Josephson junctions, and the Josephson parametric converter, which is kind of more of a resonant structure in which you can tune the frequencies with the magnetic coil that changes those. For the same way you can do a flux qubit, you can change the frequencies in here so that you can make it match the signal frequencies. We also have a lot of shielding. So things that we would use are cryoperm, which is this metallic stuff that repels magnetic fields. We would pot all our signal lines in light tight EchoSorb here, because infrared radiation, that is even just the black body radiation from inside the fridge, can negatively affect the qubits. We package these into printed circuit board type things with signals, essentially coax. You have coaxes into these things and coax out of these things. So you have all these kind of coax signal lines, which are just like your cable TV at home, except a little bit smaller to support higher frequencies. And they interface with these packages, which have wire bonded to the chips themselves. And so in that way, we can isolate them while getting good signals to them. And so kind of let me present an outlook to the kinds of things where we're looking at improving. So one of the things is where we eventually want to get to is having cryo CMOS controls. So we could generate our signals inside of the fridge. Now, it's really hard to do that at the lowest temperature stage of the fridge, because that's where the qubits live. We don't want to bother them. But at the 3 Kelvin stage, where we have these pulse tube compressors cooling that stage, we have a lot of cooling power there, to about 2 watts per pulse tube compressor. So you can just keep adding to pulse tube compressors, and you can support the cooling of the electronics, so that if you engineer it correctly, you can get CMOS electronics working at these lower temperature stages. We have a lot of coax cables in here. That's kind of annoying. So what we could do is kind of make flex cables that have like low crosstalk, but yet can support very good signals between these stages, and have the correct, I guess, cryogenic properties for whatever stage they're connecting to. We can build, there are these bulky ferrite materials like our isolators and circulators, the things that route signals and protect signals from going different ways, are typically made out of very heavy magnetic things, which are pretty bad for this cryogenic environments and for the qubit environments. But we can actually use the Josephson parametric converters, for example, to get the same kind of performance out of superconducting based type devices. So we want to be able to eventually replace a lot of these things that do the routing with smarter ways of doing things. At the same time, our quantum processors live in this can, and we are always investigating the coherence, the junction materials. So there was a question about materials earlier. One thing we'll do is look at the queue of materials to see how good we are. We're looking for like oxides that can present defects at different places in the surface, inside the junction, and can affect essentially be decay channels for our oscillations. Yeah. Excuse me. We're also always investigating 2-qubit gates, so we can think about how we can improve upon cross resonance, and we've done some bit of that and published it about, like, say, direct cross resonance, for example. Well, I didn't get into the details of what's different, but we'll worry about that if there's a question. We can also come up with different couplers, so we can realize different types of gates as well. So we might want to figure out ways of canceling interactions we don't want while promoting actions we do want that generate entanglement the way we want it to do in a controlled way. We also have, like, say, next generations of room temperature electronics. So this is a newer one, kind of current. And then here, each one of these modules is about a third of the size of a pizza box and still controls the a single qubit. So you can see how many more you can get, like 50 qubits on a rack now instead of 20. So you always got to think about the classical footprint it takes to control and operate the quantum computers as well. So that's important to remember. And so that brings us to kind of our roadmap. We have a software on top and a hardware on bottom, and I'll kind of just talk about the hardware one first. So this year we've promised to release the Osprey processor, which is 433 qubits for this year. So that will be out soonish. And then our original roadmap had us achieving 1,000 next year on the Condor, but we have a newer roadmap that has showed us where we want to introduce modularity into this kind of heron, where we can make classical connections between different processors and also quantum connections between different processors, and come up with novel ways of modularizing the systems so that we can get to 4,000 plus qubits in 2025. So it's been a while since I worked on the hardware, but I worked on the Falcon and the Hummingbird processors back in the day. So now I work more on the software side. I'm actually more of a consumer of the software side. We have a lot of circuits for, Qiskit, our open source software framework for quantum computing, so that you can control all these things from the comfort of your own home or wherever. And you can run all the algorithms that you might want to do. For example, machine learning optimization. I do a lot of quantum simulation stuff, which maybe I'll show if we have time. We also have runtimes for ways that we can extend quantum computing, or we're looking at extending quantum computing to an orchestration level with, say, classical HPC, AI, GPUs, what other kinds of quantum computing resources that can be used and orchestrated. So we're going towards this kind of serverless model of quantum computing, of which Qiskit runtime is the first step. We have dynamic circuits, which are coming out this year as well, which are going to allow you to be able to make a measurement and do a condition within a quantum circuit itself, which is pretty cool. I know that's very difficult because the control electronics and compiling and control flow is very stringent to be able to allow to do that. And then we're getting to this kind of serverless thing where we have the orchestration, we have toolkits that do a lot of the work for you, so that you can extract the most out of noisy quantum systems as we move to quantum error corrected type devices in the long term. And so the kinds of metrics we think about, like when we're building these things in the lab, is we think about the frequencies at which we generate the control. So these are the kinds of things we classify our qubits as. We look at the information that's limited by decoherence. So our decoherence times are typically, say, 150 microseconds or so, but we've shown up to a millisecond on some test devices. Our measurement is getting better. We can do single shot measurements, which means we can accurately measure a qubit in the 0-1 state to within 1 or 2% at this point, using those fancy amplifiers I talked about. But yet our gate speeds will be limited by the kind of anharmonicity. So sometimes we do have to worry about the higher order levels of the transmon, because we can get leakage to those states if we try and do things too fast. We're also always going to be limited by how much we couple our qubits together. That's going to limit our 2-qubit gates speeds as well. And so let's see. I don't know how we're about time, but I can talk a little bit about what I've worked on, and maybe just like 5 more minutes or something. What do you think, Michelle?
Yeah, I think that's fine. Our next session is at 5, so you have another hour.
Yeah, I don't think I need another hour, but I'll just kind of go through like 2 more slides and then skip to the end, I think.
Yeah, I think that sounds great.
I think that'll be a good thing. So, basically what I've been doing since I came out of the, being an experimentalist, is I have a lot of experience using microwave pulses. So I found it natural to use Qiskit Pulse. And I then found a home using, or I kind of found some cool projects using pulse level optimization to do quantum simulations. And quantum simulations are, close to the kinds of toy model Hamiltonians that I was learning when I was in grad school. And so this is kind of a paper that actually I just worked on, just got accepted last week. But I did it with Qiskit Nature, and I did it all within the Qiskit framework. So it's basically specifying a Kitaev, an interacting Kitaev chain Hamiltonian. I can write down the Hamiltonian in Qiskit Nature. I can use different parts of Qiskit Nature to do the Jordan-Wigner mapping. I can do use Qiskit Opflow. These are all different modules that exist within in Qiskit to do the trotterization. So within just a few lines of codes, I can go from a Hamiltonian to a circuit. And then once I get the circuit, I start doing other kinds of things where I've been working on bringing out tools to help with these, say, pulse scaling, optimization, dynamical decoupling, and things that I would want to do to a circuit to try and squeeze out the most performance from the noisy quantum computer. So in this vein, we've made an open source repo called Qiskit Research, and we're trying to educate users how to best employ it for research. So it's kind of got two things. It's a framework for it has utilities for using these kinds of. It has utilities for like not just us, but anyone who wants to use the same kind of tools that we want to do to mitigate errors, or how we think about best mapping our hardware, our algorithms to actual hardware. In addition, it hosts open source software that people use for their research projects. So you can see the notebooks that I used for that paper, for example, are hosted on there. But some of the things we think about that we want to like kind of highlight that to researchers who really want to think about these problems is like kind of noise aware circuit layout. You're going to have like a certain topology and certain individual qubits with certain error rates that you want to try and optimize for your quantum algorithm. You want to do some pulse scaling, which is something I did, which is kind of using the pulse level details to just do the amount of entanglement you need for a given algorithm, which works very well for quantum simulation algorithms. You have dynamical decoupling, which are some techniques we learned from in nuclear magnetic resonance, NMR techniques for controlling spins and stuff. You can get rid of, you can suppress the dephasing noise, for example, using these control techniques. Polytwirling is another one where you can kind of twirl over the error channels that you have in your system. So when you can average that, you can convert, say, coherent error into stochastic error that you can then average over and get an answer you want. You can mitigate the measurement errors, for example, by calibrating them and observing them. You can essentially get a classical process matrix, and then you can invert it, more or less. We have zero noise extrapolation. Well, this is not something in there yet, but another technique we use is oops. Sorry, I don't know, my PowerPoint went a little weird, but whatever, we'll just finish this. The zero noise extrapolation is a way of controllably increasing noise or making your circuit more susceptible to noise, so that you could then ask the question, what happens if I scaled that noise back to zero? Another thing, actually, one thing I just included was an estimated fidelity, so you can kind of calculate whether I can want to measure the circuit or not, or want to actually execute the circuit on real hardware or not. Like, what is the depth of circuit I am doing? I can look at the fidelities of my gates and kind of estimate. Managing data is something we keep looking into, trying to do a little bit better job of, and such. So I'll show this by example by just kind of going to the last slide. Basically, just to summarize, we believe superconducting qubits have a bright path to scalability, but because noise will be us for a while before error correction will be about, we're going to work on error mitigation to do what we can do to squeeze out as much as we can from the hardware that we have. And you can find this at this website here, github.com/Qiskit Research. And you can contact me at ntbronn@us.ibm.com. And I'm happy to answer any more questions for the next few minutes.
Do you think you can send me those links, or if you want to join the Discord and put the links in there as well for everybody to see the Qiskit Research repo and probably some.
Yeah, I'm happy to send you all the links we talked about. Absolutely.
Yes, that would be awesome.
All right. I guess all the questions got asked during.
Yeah, I think if nobody has any questions, then that will be all.
All right, well, thanks a lot for your questions, everyone. It's a pleasure to be here and happy Fall Fest.
Yeah, Nick, thank you so much. It's been really great to just hear like such a diversity of, I think, speakers working on different things. We had Sanjay also, I think, just talk about a brief intro to, quantum, and then you getting deeper into like the applications of hardware. So it's very exciting. And oh, it's just the chat message. Sorry, I'm like doing two different, obviously different things, so I have like a little scattered brain. But it was a really amazing presentation. If you also want to send me the slides, I'd love to put it in our Discord server, as well as all the resources to read later, because you have quite the breadth of papers published, and it'd be really cool for people to see your work, plus how that relates to kind of the research at IBM as well.
Absolutely. So thanks everyone for your questions, and I hope you enjoyed, and good luck with the Fall Fest.
Yeah, thank you so much, Nick. It was really great to see you.
All right, great. Thanks.
Great.
Good luck with the
Bye.
rest of it, everything.
We will.
All right. Goodbye.